Alright, welcome to Lecture 2 on atomic radii. This lecture is just going to be a continuation of our periodicity unit, and really a continuation of Lecture 1 for sure. If you recall from Lecture 1, we talked about effective nuclear charge and the shielding effect and repulsion between the inner electrons and the valence electron shells. And we're going to apply effective nuclear charge and those principles to the size of the atoms or the atomic radii. And so lecture 1 is really important in order to understand what's going to happen in lecture 2. So make sure that you understand effective nuclear charge before you go on. Our essential question that needs to be answered here in this lecture is, what is the atomic radii trend for the first 36 elements? You are only going to be required for those first 36 elements. Alright, so first of all, let's get started with looking at the units for radius. If you look here along our graph here on the y-axis, the atomic radius is measured in PMs. What does PM stand for? Well, it stands for picometer. A picometer is extremely tiny, much smaller than a nanometer even. Very tiny. So it tells us that the radiuses of atoms are really small, which should be expected because we can't even see atoms with our naked eye, or certainly not even, or hardly even with a microscope. So they're very tiny. Alright, so a definition, a good definition of atomic radii is the measure of half the distance between neighboring nuclei. Alright, very good definition. When we kind of give you a drawing of this, let's say that we have one atom and it has a nucleus in it, and then we have another atom that's bonded to the other atom. And so what we're going to do is we're going to essentially measure the distance from one nucleus, to the other nucleus. And then we're going to cut that in half, and half of that distance between the neighboring nuclei and the other nuclei is considered the atomic radius. Alright, so now let's get down to the nitty-gritty here, and we're going to look at a graph of the first 36 elements on the periodic table. And it might really be helpful for you to have a periodic table in front of you. I know I have a periodic table that I'm going to refer to as I look at this graph of the 36 elements. As you can see from this graph, on the x-axis is the atomic number, and again on the y-axis is the size of the atom, the radii of it. And so go ahead and pause this for a moment and get yourself familiar with the graph. Notice what happens as you move across or increase the atomic number. Alright, so let's look at question 3. It says, what is the general trend in atomic radii as you go down a group in Model 1, which is represented by the graph? And support your answer using 3 groups, okay? So if you look closely at the here, you will find that hydrogen is right here, and then after hydrogen right here is lithium. So we're essentially looking at group 1. So if you look at the trend in group 1, there seems to be this deal here. As we go down group 1, there seems to be a general increase in the atomic radii. This is sodium, and then right here is potassium. So as we're going down group 1, there is a definite increase in the atomic radii. And if you look at similar groups, as you go down group 2, the radius will increase. On group 13 as well, you'll see that the radius increases. Alright, so let me erase all this. So essentially, there's an increase in the size of the atom as you go down a group. Why is this the case? That goes to number 4. Using your understanding of effective nuclear charge and the structure of an atom, explain the trend of atomic radii that you identified in question 3. Well, this should be going back to look at lecture 1 now. And you know from lecture 1 that the effective nuclear charge remains approximately the same as you go down a group. Alright? So because it remains essentially the same, the reason why the atom is increasing as we go down is due to an increase in number of occupied shells. So we're just adding more shells to the atom as we go down the periodic table. In the first group, you only have one shell, but when you get to group 2, when you get to hydrogen, you only have one shell. When you get to lithium, you have 2 shells. When you get to sodium, you have 3 shells, and then potassium, 4 shells, rubidium, 5 shells, cesium, 6 shells, and finally francium, 7 shells. So we're just adding more shells, and so the valence electrons are getting further from the nucleus, and therefore you see an increase in the size of the atom. What about going across from left to right? What happens as you move across the periodic table? Well, if you look closely within a period, and so here's period 1, here's period 2, period 3, period 4. Generally, as you go across a period, there seems to be a decrease in the radius. It's getting smaller. So it's just the opposite of going down a periodic table. Remember, when you go down in a group, the radius increases, but as you go across from left to right, it's decreasing. Now, why is it decreasing? What's causing that decrease to occur? Well, it is because, if you remember, that as you move left to right across the periodic table, the attraction between the nucleus and the outer electrons increases as the nuclear charge increases. So, because the nuclear charge is increasing, there's a greater attraction on the valence electrons. So the valence electrons are going to be attracted to the nucleus strongly, and therefore the radius is going to start shrinking. It's going to get smaller. The radius is just going to get smaller because the nucleus is going to attract those valence electrons with a stronger force of attraction, causing the radius to eventually get smaller and smaller as you move across the periodic table. So let's just kind of review really quickly here. Alright, so let's just kind of take a moment and review the atomic radii. So first of all, the atomic radii is going to increase. It's going to get larger as you go down a group from top to bottom. And that is because you are adding more electron shells as you go down the periodic table. As far as going across the periodic table, across a period left to right, the radius of the atom is going to get smaller. And this is because the effective nuclear charge is getting bigger, or getting greater. That means the electrons, the valence electrons, are going to be more attracted to the nucleus, and therefore the nucleus is going to pull those valence electrons closer to it, causing a smaller radius to develop. Alright? So those are some important ideas about atomic radius that you should know. Alright, so now let's go and look at ionic radii. All right. So we've looked at the radius of atoms that are neutral, and now we need to look at the radiuses of atoms that are ionic, okay, that are ions essentially. And so let's take a look at the general idea. If you have a neutral atom, say like sodium, and you have a sodium ion, the difference between these two is that the sodium ion loses an entire shell because it loses one valence electron. And when it loses an entire shell, it's going to have a smaller radius. So essentially, more positive ions are smaller than their parent atoms. And this is due, and I would make a note of this, is due that positive ions lose an entire shell when they become an ion, making them smaller. All right. On the flip side, negatively charged ions are larger than their parent ions. And why is this the case? Well, let's look at chlorine. If chlorine gains an electron, it's going to cause more repulsion in that valence shell. So the valence shell is going to get bigger in a negatively charged ion, creating a larger radius for that ion. All right. So we kind of look at this a little different. Okay. When a negatively charged ion is formed, which is an anion, when that anion adds extra electrons to the valence shell is going to get bigger because of more repulsion. And therefore, the size or the radius of anions are larger than their parent atoms. All right. So again, let's summarize there, is that metals lose electrons, so they lose an entire shell. And so positive ions or cations are smaller than their parent atoms because they lose that shell. Whereas anions are larger than their parent atoms because when we gain more electrons to the valence shell, the repulsion forces are going to make the valence shell larger, increasing the radius of those anions. Alright? So that is it as far as atomic radii are concerned. In fact, that is it for this entire lecture 2 on atomic radii. So I would go back, review this lecture carefully, make sure you understand the trends of atomic radii and why those trends are occurring. The why is so important because on the test you're going to have to explain the why they're occurring, and for the quiz as well. And make good notes, and other than that, we are done with this lecture.